All right. When's your first test coming up?
Tuesday?
This Tuesday.
Tuesday.
The upcoming Tuesday? Okay, okay. And it covers the first three, including kinetics? All right. Um, I'm going to try and see if I can. Do you guys feel like you need a review of the first three chapters? Yeah? All right, so if it's a review for the upcoming test, would that be helpful?
Yeah, maybe like a couple questions for the
Okay,
different topics. Yeah, just practice.
sounds good. Um, I'm not gonna bother like doing it live because we all will have different times. I'll just record it and post it. Uh, yeah, no promises. This is gonna be unpaid, but I have a lot of like private clients that I tend to, and so if I have time, I'll most surely do a
Just, I
little.
mean, whatever you can do.
Thank you. Okay, okay. Let's see. All right, let's get started. All right, thank you for waiting. Where are we? Actually, station and yeah. Oh, someone asked where to find the recitation notes. Right here. Sorry, right here. Zoom, YouTube, notes. Was the E? No, that was Jonathan. He's not here. Okay, cool. Well, it will be in the recording. Um, all right, let's get started. Kinetics today, we answer the question of how do we talk about how fast a reaction is proceeding, and more importantly, given the initial concentration of the reactants, can we predict how fast the reaction is going to go, just based on that piece of information and one extra piece of information. Okay. All right. So kinetics. Three main topics in kinetics. The first is relative rates. Right. In a chemical reaction, you have a bunch of reactants, a bunch of products. They may all not be getting consumed and produced at the same rate. Some may be getting consumed or produced faster than others. So how do we relate the rates of one species to another? It's pretty simple. Um, so yeah, that's the first topic. By the way, in this chapter, we're going to note rate by ddt, rate derivative, time derivative. And if we're talking about species A of A, so rate of change of the molarity of A. And yes, molarity is denoted by the square brackets. Cool. So let's. I'll just demonstrate this with a nice example. C6H12O6. So let's burn some glucose. 6CO2 and 6H2O. Now, if you want to relate the DDTs of each of these species, you have to sort of standardize them, right? The first distinction that happens between reactants and products is, well, reactants are getting consumed, products are getting produced, right? Particularly, these have negative rates of changes because they're going down in amount and molarity equivalently, and these have positive. All the products have positive rates of change, and so you want all of it to be standardized, and also different things have different coefficients. So not only do you want to convert everything into positive numbers, you also want to get rid of any leading coefficients. That's how you standardize all these rates. So let's begin. The idea is reactants get negatives and you divide out the coefficients. So I'm just going to write down the rates first. ddt of C6H12O6, ddt of O2, ddt of CO2, and ddt of H2O. All right, let's begin. You tell me the coefficients, all right? I'll start with the first one. It's a reactant, so I'm going to put a negative. There are no coefficients, so I'm just going to leave it at that. Right? You divide out the coefficient. All right, can someone tell me what's next?
It's a reactant, so it's gonna be negative.
Uh-huh.
And then there's gonna be a 1/6.
1/6, cool. Right, Grace, next.
Okay, so products.
Mm-hmm. So
Yeah.
positive.
Yeah. Plus
Mm-hmm. And then you divide out the coefficient.
1/6.
Excellent. All right, Alexandra, last one.
Positive 1/6.
Yep, same deal. Cool. So that's how all of these are connected to each other. And all of these standardized numbers, that's what we call the rate of the reaction. Rate of reaction. Just more notation. This you would call the rate of consumption of glucose, rate of consumption of oxygen, rate of production of CO2, rate of production of H2O. Here's a question.
So sorry, would we
Mhm.
write like -1, -1/6, or would it be -1/6 derivative of -1/6?
Oh, so the number always comes first. The number is a multiple. So this whole thing is a single, it looks like a lot of notation, but it's actually just a number at the end of the day. It's a single piece. So you're multiplying -1/6 times whatever that number is. Was that your question?
Yeah, sorry, what is that number?
It's just a rate of change, slope.
Oh, okay.
All right. So for the given reaction, blah, 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 if nitrogen gets produced at a rate of 3 molars per second, you see where the unit comes from? This is molarity, so that's big M. Unit of time is seconds, so molars per second. If N2 gets produced at a rate of 3 molars per second, 2 questions. How fast is H2 getting produced? So the rate of production of H2, and then lastly, determine rate of reaction.
this one? Is it 1 molar per second?
Is it 1 molars per second? Let's see. So that could be true, but let me check. Whoops. Let me help with that. All right. All right. So let's write all of these givens in the notation that we're after. So N2 is getting produced at this rate. Getting produced at this rate. So what is 3? In the notation of everything that appears in this equation, what is 3? What is 3 equal to? I'm sorry. I'm pointing at the wrong equation. Okay, sorry. Let's set up the equation for this reaction to begin with before we answer this question. Okay. Yeah. Alexandra was horrified. I was like, what's going on? Okay, yeah. All right, so I'm just going to set this up real quick. ddt of NH3, you know how to do that. Positive ddt of N2. And lastly, positive 1/3 ddt of H2. Cool. Now, in the notation of this one, what is the number 3? Let me simplify it. Which of these chunks is 3?
The hydrogen.
The hydrogen. Let's see. If N2, that is our eventual answer, right? That's the eventual variable that we want to find out. How fast is? Okay, so I'm going to write that down real quick. ddt of H2 is what is to be found. Okay. What is 3 then?
The rate at which nitrogen is being produced.
Exactly. So in the notation of this equation, what would that be?
ddt N2 equals 3.
Exactly. ddt of N2 equals 3. Right? Rate of production of nitrogen is 3. That's what this question's saying. Also, it is positive 3 because it is production. Okay, I'll give you another example after this. All right, so we now go equation hunting. We want ddt of N2, so that's this part, and ddt of H2, which is this part. So we just focus on those two. I'm going to peel that apart from the main equation and write ddt of N2 is related to H2 as 1/3 ddt of H2. And all we now need to do is to solve for this chunk, which is right here, which is like multiplying both sides by 3 to get rid of that 1/3. And so 3 times ddt of N2 is ddt of H2. Plug in your numbers. Three times, what was it for N2? 3 times 3, so it comes out to be 9.
Abdullah, but wasn't 3 the rate of production of hydrogen, why is it not 1, the rate of production for it?
No, if N2 gets produced at a rate of 3 molars per second.
Okay, never mind.
Yeah. 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 I'll give you one more example on the same, a follow-up to the same question. So this idea gets hammered home. Okay. All right, so let's top this off with determined rate of reaction. Remember, rate of reaction is just equal to these common numbers. And so you can just choose any one of them and relate it to the rate. Since we have information about ddt of N2 there, so rate equals, one way to write rate is ddt of N2, which we had in the question to be 3 molars per second. And we're done. Okay, there's too many lines going on here.
How is it that it's what was given in the question? It's not more complicated than that.
Coincidence in this question. So for example, I could have also, it's also my choice, right? I chose to relate rate. Rate is equal to all of these things, right? And I chose to relate it to this thing. As it so happens, there's nothing in front of it. It's just a positive, right? There's no division, there's no coefficients. So I got lucky. But so now suppose I had chosen to relate rate to the rate of production of hydrogen over here. Then it would be rate equals 1/3 ddt of H2, which is 1/3. What did we find ddt of H2 to be? Times 9, which still gives you the same number.
Got it. So it's not like there's an equation for this
No.
part. It's just identifying from the original one.
Yes, this is the only equation you have access to.
Got it. Thank you.
Mm-hmm. All right, last follow-up. If NH3 is getting consumed at a rate of 200 molars per second, determine the rate. So I'm going to word it in two ways. Determine the rate of consumption actually, let me just say that. Determine the rate of consumption of H2. Yeah, rate of consumption of H2. Cool. So we want to relate the NH3 to H2, and those were, if I remember correctly, were related as -1/2 ddt of NH3 equals 1/3 ddt of H2. Now here's the kicker. ddt of NH3, the number, I agree, is 200 molars per second, but it is the rate of consumption. So you want to introduce a negative sign. Okay, that's all. The rest is the same. Negative 1/2 times negative 200 equals a third ddt of H2. So this makes it positive 100, and then multiply both sides by 3 ddt of H2. And you're done. Which is 300. Oh, sorry. The rate of production of H2. H2 is a product. Basically, the whole idea of me going over these questions, the math is extremely simple. It's just translating words to proper signs. That's the only thing that people get caught up in. Okay. Any questions?
Yeah, a quick one back to the B. If we would have picked the other portion, like, are they meant to have the same rate, like, regardless of what we pick, or no?
Yes.
Yes.
They're all equal to each other.
Okay. Okay.
Right? Rate equals...
So that's like a good check that we could do.
Exactly. Rate equals that, or alternatively that, or alternatively that. This is like 1, 2, 3, 4 times 4, 16. These are 8 equations in total.
Got it. And they should all be 3. They should all
Yeah.
equal to 3.
Exactly. Yeah. Yeah. All right, so that's all there is to know about relative rates. Moving on is the rate law. The difference between rate law and relative rates is that relative rate relates rates to rates, right? Rates are connected to rates, right? Every single thing in this equation is a rate. So it doesn't really do anything fancy. It just says that, hey, you have a chemical reaction and it has a certain stoichiometry, right? It has a certain coefficients for each species. Well, if that's the case, then the rates should behave like this. If you know the rate of one thing, you need to know the rates of everything else because they are so rigid. The stoichiometry makes it work. So the rates are related to rates in relative rates. In rate law, however, this is the real useful one, is that rates are related to concentrations. And the idea is very simple. Suppose you're carrying out a certain chemical reaction, and by some magical ability, you take a snapshot at a certain time, and you are able to figure out exactly what the current concentrations of each reactant are. How much of each reactant is in there, right? Just using those numbers, you should be able to calculate the rate of the reaction. That's the idea, okay? Specifically concentrations of reactants, that's all we need. And the general form of rate law is that the rate of the reaction equals this constant K times the concentration of the first reactant. So you basically multiply all the reactants together, their concentrations. Let's put 3 of them, doesn't matter. Usually you just have 2 reactants. And then they're raised to some powers. Let's call them M and Mn and, or let's just call them M1, M2, and M3. Right? A constant times molarities of the reactants, each raised to some arbitrary power. K is called the rate constant. If you keep the environmental conditions of the reaction the same, like keep the temperature, etc., the same, you don't add any catalyst or anything like that, then the rate constant for a given chemical reaction will not change. It's just a constant. It's a number that you can determine experimentally. Within each bracket are the concentrations that you're familiar with. These numbers powers, so this power is on reactant 1, right? So M1 is called the order of the reaction with respect to reactant 1. Follow the same pattern and tell me what M2 would be.
It's order of the reaction with respect to reactant 2.
Exactly. M2 is order of the reaction with respect to reactant 2, and I'm not going to write the last one. So it's just that. And then finally, if you add up all the powers, M1, M2, and M3, you've learned this in class. What is this called? You haven't. Say that again. Overall, yeah. So it's the order of the overall reaction, or overall order of the reaction. Right, it's for the whole thing. All right, so there's that. Two kinds of questions from this section. One super easy. The other one is something that the procedure for which you want to know how to do. The first one is pretty simple. A certain reaction, no. The following reaction is order 2 with respect to N2 and order 1, no, actually order 0 with respect to hydrogen. And this is the reaction. N2 plus 3H2. Let me take that out. That's foreshadowing for the next chapter. Okay, yeah. If at a given instance the concentration of N2 is 2 molars and the concentration of H2 is 3 molars, determine the rate of the reaction. At take K to be 4. K has units. I'm just not going to bother talking about that right now, but I'll discuss it at the end. Take K equals 4. All right, so let's take a look at this equation and give me the form of the rate law. So I'm going to start with the first thing. Rate equals, what comes next?
Four.
4, good, times. Before we plug in numbers, let me just write the generic one. So you have some rate constant K. Our reactants here are N2 and H2. And then they should have some powers. Let's just call them M and N. Okay, so like Alexander said, this is 4. All right, what's next?
You would write the concentration of N2, but since it's in second order,
Mm-hmm.
I would write 2 there.
Yep. Followed by
So H2 is 3, but
Yep.
it's 0 order.
Yep, to the power of 0.
You could maybe just write 1.
Yeah. Anything to the 0th power is 1 except 0. 0 to the 0 is a monster, undefined, bad. But you'll not be given a question that involves that. Okay, so that just is 1. All right, so 4 times 2 square, also 4, 16 molars per second, since it's rate. So it's a plug and chug problem at the end of the day. I just wanted you to get familiar with the terminology. Yeah. Okay, cool. All right. Yeah. Rate always has units of molars per second. Concentration, which are the square brackets, always have units of molars. The rate constant K actually doesn't have any set units. Its units depend on the order of the reaction. And I'll discuss this a little later. Okay. All right. Cool. The second and more important question within this topic is determine the rate law. And that what that means is calculate the constants in the rate law. K is one of the constants, and the powers are the other constants. The values of K, M, and N is what you're trying to find. Okay. All right. Cool. So here goes a question. Consider the following initial rates for various possible concentrations. Let's just do 2 reactants first, N2 and H2, and the rate. Okay, so let me start like this. Let me say that this was 2, this was 1, now it was 4, and it was still 1. The rate jumped from 3 to 4. So 12. Yeah. And then lastly, let's make this 2, and let's make this 3, and make this 9. Yeah. There's a logic to these numbers. I'll get there. Cool. Okay. And so the question is determine rate law. Pretty simple. In every determined rate law problem, you'll always have one of these tables given to you. Now the idea is just go ahead and apply the rate law to each of these 3 instances. Okay, so before I write my rate law, I need to know what my reactants are. Anyone? N2 and H2, yep. Good. N2 and H2 are my reactants. So the generic rate law looks like rate equals some number k, which we don't know yet, times N2 to some power m, times H2 some other power n, and that's it. Cool. So look at the first row and basically plug in all the known values into this equation. So in the first thing, the rate is 3, so 3 equals k, unknown. Concentration of nitrogen is given to be 2 to the power of some m, which I have no idea yet. Concentration of hydrogen is given to be 1 to some power n. All right, forgive me, but I am going to change the numbers ever so slightly. I'm going to make this 1.5, 1.5, and the last one 4.5. Yeah. All right, so I'm going to change that to 1.5. All right, so that's the first one. All right, somebody tell me what the next one would look like with the values plugged in. Grace, take a try.
Sure. So 12
Mm-hmm.
equals k 4m
Mm-hmm.
with the m, 1.5 to the n.
Excellent. All right. Pavel, I haven't heard from you. Last one.
How am I coming in? Can you hear me?
Yep.
The last one would be 9 equals the rate constant times the concentration of N2, which is 2, raised to m, and then 4.5 raised to the power n.
Oh, I thought I heard you say the numbers
No.
as I wrote them down.
I was just saying what you were writing down. Close enough. Yeah.
Okay. Oh man. All right. Cool. And so now we have a set of 3 equations, 1, 2, and 3. And we have 3 variables to solve for, k, m, and n. So it should work. If you're solving for n variables, you need n equations. When you're solving for these 3 constants, you should always proceed in the following order. First, solve for the powers, and then solve for k. It makes your life a lot easier. Powers first, constant last. And to do this, you want to start by choosing 2 rows for which one of the values is fixed. If you look at the first 2 rows, Hydrogen isn't changing, so that's good. So we can do that. Let's choose 1 and 2. So you choose those two, and then you proceed and you divide those two equations. So our first choice is 1 and 2. Well, they're right here, so I'm just going to insert these things. All right, so what do I get out the other end? 3 divided by 12, 1 over 4. The k's cancel because there's a k upstairs and downstairs. There's a 2 to the m divided by 4 to the m. They have the same power, so I can sort of take out the power. And then the last one just cancels because the same thing up and down. 1.5 to the n, 1.5 to the n. So that's all I'm left with. Let's simplify this a little bit. 2 over 4 is 1/2. What power of 1/2 gives you 1 over 4?
Power 2.
Power 2. Right? 1/2 times 1/2 is 1 over 4. Cool. So we conclude that m equals 2. Now there are some of you out there who don't like this guesswork. What power of 1/2 is 1 over 4? And if you want to do this purely mathematically, let math do all the work, this is what you do. Can you think of a function that brings down the power? Yes, Pavel.
You say you haven't heard from me, so here you go. The inverse, you raising to the -1. Or wait, no, I'm wrong. I'm sorry. Brain fart.
Inverse was indeed. You're right. It is inverse. It is inverse. It is inverse-ish. Let me say that. The inverse of a power is the root, right? Nth power, nth root. They cancel each other out. There's something that brings down the power. Okay, let me do this. Powers are sort of like exponentials. What is the inverse of an exponential? Pavel, take a try again.
The logarithm.
The logarithm. If you hit both sides with a logarithm, it will bring down the power. So if in general, so okay, for example, ln of 1 over 4 equals ln of the whole thing, but knowing the properties of logarithms, you can bring down the power. So it's going to be m times ln of 1/2. This is just a number that you can calculate in your calculator. Let me call that star. This is another number. Let's call that that. And so m, just divide both sides by that. Done. So if you don't want to do the guesswork, and sometimes you don't, because sometimes you'll have shit like 0.49 equals 0.7 to the power of m. I mean, it's sort of silly. You can still tell that it's 2, but it's like, if they're like weird numbers, it becomes harder. So logarithm to the rescue. Okay. All right, so give me 2 other equations that we can use to, so we've solved for m. Give me 2 other equations that we can use to solve for n. We've held h2 to be the same. Now hold the other thing to be the same. Yeah, I thought I heard.
1 and 3.
1 and 3. I like that. Yes, so let's do 1 and 3. Great. All right, Alexander, since you chose the 2 equations, give me the rest of it.
Okay, so we divide the 3 equals k 2
Mhm.
to the second,
Yeah.
or to the, second power
Uh-huh.
times 1.5 and divided by 9 equals k to the times 2 to the second times 4.5 times to
Good.
the n.
And tell me the simplified answer when you divide.
Got it.
Okay.
So it's gonna be 1/3
1/3.
equals k.
Those cancel.
Oh, those cancel. Sorry.
Yeah.
And then it's gonna be 4 so 1
Mm-hmm.
times 1.5. Oh, I don't know what 1.5 divided by 4.5 is. Sorry.
Yep. So just that.
To the n.
Yeah, to the n. Excellent. It's 1/3. Yeah. All right, so what must n be? This one's trivial. Adam?
Sorry, that would have to just be 1.
Yep. Exactly. Done. Excellent. So m is 2, n equals 1. And now the last thing that we need is k. Choose any single equation, plug in everything, m and n included, and solve for k. All right, Christopher, choose an equation.
Like one of the 3, 12, and 9s.
Yep. The choice is completely arbitrary now.
9 equals k
Sure.
2 molar, or 2 to the m,
Which is?
2.
Yeah.
And then 4.5 to the 1.
Mm-hmm. All right, so n equals k, 2 squared. That's 4 times 4.5. No idea what that... Oh! There is an... Okay. I was going to touch my calculator, but why do that when this 4.5 goes twice in 9? And so that's 1/2. That's 0.5. Okay. Yeah, works. Yeah, so k is 1/2. And once you have all your constants, you rewrite the rate law as rate equals n2 is your actual variable, m is 2. Oh, sorry. Start with k, 0.5 times n2 to the power of 2, h2 to the power of 1. And that is the final rate law. Yeah. I'm happy the numbers worked out because I basically was doing all of this in my head to come up with these numbers. Because if you choose any random numbers, the m, n, and k, m and n will come out to be non-whole numbers. So there's that problem. And so you have to choose very specific numbers. Yeah, Christopher?
For this class, are we always going to get a chart where there's going to be a point where A is constant and B? Because there were some homework problems that
Yes. And just so we have it handy, someone brought this up last semester that I taught this class. I'm just going to put... hold on. Let me stop sharing my screen real quick. I have a YouTube video on it. that I'll put in Slack. Yeah, and you can watch it on your own time. All right. Excellent question. Just to reiterate the question, we were looking for two rows in each case where the numbers matched, right, for one of the reactants. Sometimes that doesn't happen. What do you do in that case? And so that is answered in sort of low quality, yes, variation, this thing. Let me just share the thing. Yeah. Okay. Cool. Another possible variation on rate law is when you have three reactants. Right? In that case, let's say you've got A, B, and C, three reactants, and you'll have a set of, bunch of equations. But the idea is very simple. You want to hold two of them sort of hostage at a time. Choose two rows where both A and B match up, and C is different. So the A's cancel, the B's cancel, and then it's only C that survives. Right? Then go for B and C constant. And lastly, A and C both constant. Does that make sense, everybody? Okay, perfect. Because Professor Wright has been known to give 3 reactant questions at a time. Okay. All right, so last part of the thing is integrated rate laws. As the name suggests, it's just the rate law integrated on both sides. The rate law is a differential equation. If you integrate both sides, well, it's legal to integrate both sides. That's all I'm saying. And so the idea here is that if you know the initial concentration, you can figure out the concentration anytime later. So this gives you predictive power in time. Okay. This gives you predictive power in time. And here's the setup. We'll look at a specific reactant A that has an order m with respect to it. We're looking at a single reactant with some order, right? A0 simply means initial concentration. And just A means concentration at some time later t. Initial concentration, aka when time equals 0. Time t. And of course, t is your time. Now, the integrated rate law depends on the order of the reaction with respect to A. So we're going to look at three special cases: zeroth order, first order, and second order. And all you've got are the equations for each case. Okay, so zeroth order goes A, concentration of A at any given time is given by A0 minus KT. For first order, it is A equals A naught e to the minus KT. Another way of writing this, which is often useful, if you take the ln of both sides, you can simplify it to ln A over A naught equals e to the minus KT. And then lastly, second order, I usually derive these in class. And if you want a derivation, if you go to my YouTube channel again, my recordings from the previous recitation have full derivations for each case. But since I was late today, I will not do that. So I don't remember the second one off the top of my head. It is a useful skill to just be able to derive things from scratch. In fact, that's what I did on my Chem 2 exam. A lot of these formulas I had forgotten. So I just like quickly derive it on the side before using them. Second order reaction goes where is it? Yeah. 1 over A equals 1 over A naught plus KT. Okay. So easy. In each case, you've got you basically have four things, right? Initial concentration, final concentration, time, and K. So all sorts of questions that you can imagine from these is you have three of them and you want to calculate the fourth one, right? So those are all possible questions from this topic. So it's just plug and chug, basically. With one extra addition, for first order, you have a very nice relation between what's called the half-life and K. Oftentimes, they don't give you K, they give you half-life, and you calculate your K using this equation. Okay. We'll go over two questions. And before I go over questions, let me just, because sometimes you need to match these up to their corresponding graphs, right? What is the graph of a straight line? What is the general form of the graph of a straight line? There's many, but this is the one that I want to focus on. Y equals mx plus c, right? So if you put x on your x-axis, x goes on the x-axis, basically whatever's here goes on the x-axis, whatever's here goes on the y-axis, right? Sounds like a trivial statement, but we'll use exactly that to come up with all of these graphs. So y equals mx plus c. All right, so I'm going to write down y equals mx plus c. In each of these cases, the independent variable is t. So t will take the place of x, right? So let's match up t to x. So t should go on the x-axis. And in each of these cases, whatever's here goes on the left-hand side. Sorry, the y-axis, which is a. Okay. If I take my zeroth order equation and write it, if I swap places, it would look like this. A equals minus kt plus a naught. All right, cool. What is c in this general equation? Y equals mx plus c? Does anyone remember what c is?
The y-intercept.
Y-intercept, good. Where the graph hits the y-axis. And what's m?
Slope.
Slope.
Slope, good. Is the slope of this line positive or negative? Oh, yeah. Christopher?
The slope in the a equals negative kt.
Yeah.
That's negative.
Negative, because k is a positive number, and if you multiply it with a negative, yes, it is negative. So we start at a certain point, match up the intercept to a naught, so that's where a naught is, and then it's a line going down. That's the graph, with a slope of minus k. Okay, so that's easy. All right. You don't know these forms for the first and the second. They're not linear. They're exponential, actually. And so let's just draw some generic exponential graphs for them. T and A, T and A. Both of them start at some A naught, some initial value. And because they're exponentials, exponentials never reach 0, right? Exponentials plateau. Not plateau, but an exponential thing can never get to 0. So it will just keep getting closer and closer to 0, but never actually reaches 0. Same thing here. So both the first and the second order look alike. They're exponential decay graphs. So in zeroth order, the reaction is complete when the concentration of the reactant becomes 0. Make sense? There is a definite time when the reaction gets complete, because you see the line actually hits the x-axis and the reaction comes to a stop. But the first and the second order, the reaction is never complete. It takes infinitely long for the reaction to come to a stop. Right? So you can't talk about the life of the reaction. You can't talk about how long it takes for the reaction to get completed. Which is why we're forced to only use half-life. Half-life is something you can talk about. If anyone was wondering why the hell do we keep talking about half-life, why not just double it and call it the full life? But this is the problem. The full life is always infinite. There's no number that you can put on it, but you can only talk about half-life. So if you start at A naught, if you want to get to A naught over 2, half as much, it happens at this point, and that's half-life. Same thing here. This this is a naught over 2, a naught over 2, and so on. However, not all is lost. You can still force some of these both of these reactions to be straight lines. And how do we do that? All right, so let's actually start with the second order, this thing. And we're gonna do some clever observations. T takes the place of x, so this is like mx, right? Which means the other thing should be your intercept. This is your c. Which means this whole mess here should be your y. And so if you draw a quick graph with t versus y is now 1 over a. You start with the intercept 1 over a naught, and then you steadily go down from, no, actually you steadily go up, because the slope is positive, right? Positive k. Slope is positive k. So this is, each of the blue graphs are a versus t graphs, right? Y versus x. This, the black ones, for the second order, you get a straight line if you plot 1 over a versus t. That's the idea. All right, let's finish this off with the first order. Any questions so far? Yeah. Pavel, go ahead.
Yeah, thank you for yeah, I have a question. Maybe I kind of missed your introduction of this concept, but because I see how you're breaking them up into 0, first, and second, and you can treat them all as individual concepts. Is that the idea, or is this is there a bigger picture that you introduced in the beginning before you started breaking it down into the 3 concepts?
Any given chemical reactant can have whatever order. And we, in this class, are only going to focus on the special case when the order is 0, the order is 1, or when the order is 2. Yeah.
Okay.
Yeah. So a question will specify, here's a reactant, is second order with respect to the reaction, with respect to the reactant, and then blah, blah, blah. And so you're going to go ahead and use the second order equation for that question. Yeah, so that's the idea. All right, so let's end this whole thing by taking a look at how do we convert the first order equation into a straight line. Ln of a fraction is ln of numerator minus ln of denominator. That should be familiar. So I can just rewrite the top thing like so, and then add this to both sides. All right, y equals mx plus c. T is always our x, so minus k is the m. And so ln of a naught is your c, and this is your y. So now if we plot time on the x-axis, the thing taking the place of y is ln of a. We start at ln of a naught, that's our intercept. Tell me, positive slope or negative slope? Negative slope, great. Slope is negative k. Okay. So to recap, the graph of A versus T is linear for zeroth order. The graph of A versus T is a decaying exponential for first order, and the same for second order, A versus T. If you want straight lines out of first order and second order, first order you get a straight line if you plot ln A versus T, and second order you get a straight line if you plot 1 over A versus T. So that's the whole summary. All right, I'm basically going to give you one question and end it there. Actually, two questions. Bear with me. A certain reactant has initial concentration of 2 molars per second. Actually, let me make it 16 molars per second. If the reaction is first order with respect to this reactant, and and the half-life is 3 hours. Two questions. Calculate the concentration of the reactant $12 later, and B, calculate the concentration 13.5 hours later. All right. I'm going to ask you to use the equation here, but do not use any equation in the first one. No equation, just like Ben Shapiro says, facts and logic. If anyone follows him, I don't know. He's a meme. Okay. So what does it mean for the half-life to be 3 hours? Oh, by the way, initial concentration of 16 molar, not per second, just 16 molar. Yes. Half of the substance to be gone. So if we wait 3 hours, what's going to be the concentration of the reactant? 8. Okay, cool. Is there a nice relation between 3 and 12? Can I get to 12 just by waiting a bunch of half-lives? Yes, you can, right? They're multiples of each other. All right, so let's see. 4 3 hours is 12 hours. Right? Okay, so let's start the logic here. I start with 16 molars. I wait 3 hours. As Adam said, I get to 8 molars. What happens if I wait another 3 hours? 4, another 3, 2, and another 3, 1. How long have I waited total? 12 hours. Bingo. Right? So sometimes you can solve these questions just by using logic. Just wait a number of half-lives and you can get to your target waiting time. Part A is an example of that. Part B is an example of where that's not possible. You can't get to 13.5 just by waiting a bunch of 3 hours. 13.5 is not a multiple of 3. So you're forced to use the equation. That's all. All right, so I'm just going to write ln of, or I'm going to use the first one, a equals a naught e to the minus kt. All right, so fill in the blanks for me. What's a naught? (16). Okay, e to the minus. I know t, what t is. T is 13.5. What is k? Alexandra? So half-life is 3. K is the rate constant. No, half-life is t half. Exactly. Yeah. So you want to exactly. So you want to calculate your k first. Yeah, and then plug it in. And then you're done. Any questions? All right. Absolute last topic. What is the unit of rate constant? Okay. So this will take 1 minute. Rate constant unit. And we'll talk about what is it in 0th order, in 1st order, and in 2nd order. You're going to help me with 1st and 2nd. I'm just going to do the 0th one. Okay, so 0th order something looks like this, right? Rate equals k, concentration of something to the power of 0. Agreed? Okay. We know rate always has the same units. It's molars per second. And we know concentration always has the same units, molars. So molars to the 0. To figure out the units of k, you just need to solve for k in terms of units. What's m to the 0? 1, so that goes away. So the units of k are just molars per second, and you're done. In 0th order reactions, k takes the units of molars per second. All right. Grace, help me out with this first one, 1st order. How do I change this, the rate law equation? One over molar seconds. Almost true. 1 over second. But how do I get there? So I take this thing. Give me the generic first order rate law. Basically, how do I modify this to make it 1st order?
How do you modify it to make it 1st order?
Mm-hmm. Think about what makes this this equation 0th order. What about it makes it 0th order?
That it's to the 0 power.
The 0. So if I replace it with 1, it should make it
K a to the 1st.
exactly. And in the same way, give me this one.
K a to the 2nd.
Exactly. A to the 2nd. All right, so rate. What is the usual unit of rate?
Moles per second.
Yeah, molars per second. K. And the unit of A, concentration.
Moles per liter.
Yeah, just molars.
Or molar.
Big M, big M. We're done. All right, so can I cancel the M's on both sides? Right, it's like dividing both sides by M.
Mhm.
So these go away. And there you have it, 1/seconds. Yeah? Okay. All right, Christopher, last one.
So you have m over s
Uh-huh.
equals k m squared.
M squared, exactly.
Yeah, so you divide both sides by m over 2, or m is 2,
Mm-hmm.
1 over s times m.
Exactly. Exactly. That's it. All right, cool. I think we covered everything. Oh, there might be Jesus, Arrhenius equation. Plug and check. It's very simple. I don't know if you guys have discussed it, but the rate constant K depends on temperature, and the dependency is given by Arrhenius equation. Oh, one more thing. Did you guys discuss exothermic, endothermic, like activation energy graphs and so on and so forth?
Yeah.
Yeah, okay, give me one more minute. Let me just get that over with. So you can have two kinds of reactions, endothermic and exothermic. And the reaction logic is very simple. So the graph logic is very simple. In each case, you're going from reactant state to product state, right? Come on. All right, so there's that, and there's that. So energy goes on the y-axis. You're just tracking how the energy changes as the reaction proceeds. In each case, we will start with a certain amount of reactant energy. Let's call that R. Right, so the reactants have to start somewhere. Endo means that the energy of the products is higher than the energy of the reactants. So you end up here. Anything higher than the reactant level. That's what makes this endo. Exo means you've lost some energy, so the energy of the products is lower than the reactants. The difference in energy between the two, the product and the reactant, is the enthalpy of the reaction in each case. And then you can't go from reactant to product, like just like draw a line from reactant to product. You actually have to go through a transition state that has a higher energy than both. So in both cases, go higher than necessary and then come back. Higher than necessary and then come back. And that extra hump, that extra unnecessary hump, is called the activation energy, denoted by EA. So that energy hump is like the necessary push that a reaction needs to get going. If the activation energy is super high, the reaction proceeds slowly because it's like it's hard to go over that hurdle. And so what catalysts do is they simply reduce the activation energy. So in both cases, just reduce the hump if a catalyst is present. Without catalyst, with catalyst. And same here. Without catalyst, with catalyst. All right, just to recap, this one is an endothermic reaction without a catalyst. This one is an endothermic reaction with a catalyst. Exothermic without, exothermic with. 4 possible cases. Good? Any questions?
Abdullah, I had a question, but it's not related to this, so I don't know if we want to wait.
I'll just ask me after anybody else has a chem question.
Got it.
Pavel, you had a question?
Yeah, I know you said you may or may not want to go into that today because it may be a long discussion. What about the Arrhenius equation? Because I do recall in the textbook seeing it somewhere.
Yeah.
And it was like, what is that all about? Just if you could just give maybe like an overview instead of
Sure.
details. That would be
Remember,
really helpful.
yeah. Remember our rate laws have the rate constant K, right? It's supposed to be a constant, right? It's not supposed to change with anything. Turns out it changes with temperature. So Arrhenius equation simply tells you how it changes with temperature. It also changes with activation energy. So 2 things can change your K, temperature, and activation energy. And the thing that changes activation energy is a catalyst. It lowers activation energy. So Arrhenius equation just relates the K to temperature and to activation energy. That's all.
So it's kind of like you know why I'm confused, because it looks a lot like the CC equation.
Yep. Turns out a lot of chemistry equations have the same form as that because they're exponential equations. All exponential equations look alike. Yep, that's it. All right, cool. So we're done. You all can leave, and I will ask Alexander's question. Yep, no problem.